Hello, Iron Designer here. Just wanted to go over this mathematical problem on how to solve the stress analysis for a two-wall cylinder under centrifugal force loads. The reference for this is problem 6.60 in the Professional Engineers Exam Questions and Answers by William S. Lalonde Jr., published by McGraw-Hill Book Company, 2nd edition. So in this problem statement, it says that there's a built-up cylinder consisting of an outer shell ring of thickness 1/8 of an inch, press-fitted on a copper ring of thickness 1/16 of an inch, as shown in the following sketch on the next page. The copper ring has an outside diameter of 6 inches, and after assembly is under a compressive stress of 2000 psi. The steel density is 490 pounds per cubic foot, and the modulus of elasticity for this particular steel is 16 million psi. The question is, at what RPM will the stress in the copper ring become 0? Find the RPM. Now here is the sketch. The orange is the steel ring, the yellow is the copper ring, the green is just the hole in the center. It's a hollow construction. The outside diameter of the copper is 6 inches. The outside diameter of the steel is 6 1/4 inches. The thickness of the copper is 1/16 of an inch, and the thickness of the steel is 1/8 of an inch. To begin the solution, we need to solve this by determining the centrifugal force that's generated in theoretical terms. Even though we don't know yet the RPM, we're going to solve for the RPM until the stress in the copper ring is equal to 0, or the PSI in the copper ring is equal to 0. So in our equation here, we have F equals W over G times U squared times R squared is the centrifugal force formula, where G is the gravity, W is the specific weight, U is the radians per second, R is the mean radius of the thinner cylinder. Now to begin laying out the stresses here, we have an initial stress of 2000 psi, and that's in the copper ring. We want the final stress in the copper ring to be 0 once the rings are spinning due to centrifugal force. So we begin laying and populating the formula. We begin with the stress for the steel. That's equal to W over G times 6.28 times N. N is going to be the RPM, divided by 60 squared times the quantity together. D plus H is the outer diameter plus the thickness, divided by 2, that quantity squared. We plug in the numbers. 490 for W, 1728 times 386 for G, times 0.0523 times N squared, times 6 plus 0.125 quantity squared. That gives us 1 divided by 1360 times 0.320 times N, which will be the RPM, when we're done with this calculation, that quantity squared gives us the new value of n squared divided by 115.2 quantity squared. The stress in the copper is equal to W over G times 6.28 times N divided by 60 quantity squared times D minus H, in this case, divided by 2 for the copper quantity squared. That's equal to 558 divided by 1728 times 386 times 0.0523 times N quantity squared times, this time subtraction, 6 minus 0.063 quantity squared. Notice that the 0.125 and the 0.063 are the distances to the center line, to the midpoint of their corresponding rings, so that you are exactly on the centroid of each ring. We get equals 1 divided by 1248 times 0.310 times N quantity squared equals N squared divided by 114.0 quantity squared. Here we're going to use substitution and equalization in order to find the single value of N. We begin with equation 1, 2000. Remember, that was the original stress in the copper ring, divided by the modulus of elasticity of the copper, equals the delta stress in the copper divided by the modulus of elasticity of the copper, equals 1 over modulus of elasticity of the copper times N divided by 114 quantity squared plus XD divided by 2HC. That's going to be the difference in the diameter and the radial distance. Equation 2, 2000 divided by EC equals the change in the stress in the steel divided by the modulus of elasticity in the steel is equal to 1 divided by modulus of elasticity of the steel times N over 115.2 quantity squared minus, this time, XD divided by 2HS. The sub-equation 1A is HC times equation 1. It's 2000 times HC equals N divided by 114 quantity squared times HC plus XD over 2. Next, equation 2A is equal to HS times equation number 2, which is 2000 times modulus of steel divided by modulus of copper times HS equals N divided by 115.2 quantity squared times HS minus XD over 2. The next substitution we make is equation 1A plus 2A, giving us 2000 times HC plus the quantity 15 divided by 8 times HS. This in turn gives us the equation 2000 times 0.0625 plus 0.2345, giving us the equation N divided by 114 quantity squared times the quantity 1 divided by 1.02 times 0.125 plus 0.0625. Finally, we have the equation solving for n equals 1140 times the square root of 20 times 0.297 divided by 0.185, resulting in 1140 times the square root of 32.1, giving us n equals 1140 times 5.67, which equals 6,450 RPM. In this next slide, what I've done is put the values into a spreadsheet to verify the subsections of the equations, and you can see I've included the wall thickness of the inner cylinder, the outer cylinder, the material of the inner, the material of the outer, the modulus of the inner material, the modulus of the outer material, the OD of the inner, the ID of the inner, the OD of the outer cylinder, and the ID of the outer cylinder, the density of the inner material, the density of the outer material, the contact pressure, the value of pi, the cubic inches per foot, and G, the gravitational acceleration. On the right side, you are wondering what is HS and HC. You can see that HS is similar to the wall thickness of the inner cylinder, and HC is the thickness of the outer diameter under pressure. And you have the ratio of EC over ES times WS. And we have some additional calculations in the next slide that needed to be done in order to compute the minor values within the equations. The subcalculations here show that when we pre-compute the steel, we have the values in that row 0.000734624. We pre-compute the values for the copper, and then we have the value 0.10466667. We have the values for the ring to the midpoint of the ring. We have the computed internal reduced diameter for the copper OD under stress. And then we have the ratio values. 1.875 is the ratio values of the modulus of elasticity for copper compared to the modulus of elasticity for steel, 1 divided by. Next, we have the values checking for copper and the values checking for steel. On the right side are just the tabular portions of the equations being computed in the spreadsheet. And you'll notice that in the end, the value computed numerically in the spreadsheet is slightly different. It is 6,265 RPM, a bit of a difference from the theoretical formula computation of 6,450 RPM. So this concludes looking at this calculation, and thank you for viewing the video. If you like this content, please subscribe and give us a like, and we will provide you with additional content such as this.